A power transformer is one of the most critical machines in the electrical grid. It silently does its job every day, making sure the electricity generated at power plants can travel hundreds of kilometers and still be safe to use in our homes, offices, and factories. What you are looking at right now is a cutaway view of a high-voltage power transformer, and the glowing colored lights represent the flow of electrical energy moving through it. Let quotas start at the top. The tall, black and white structures are called bushings. These are insulated terminals that allow high-voltage electricity to safely enter and leave the transformer tank without causing a short circuit to the grounded metal body. The blue and yellow pulses you see climbing up the bushings show electricity entering the transformer from transmission lines. The voltage at this stage is extremely high, often 132,000 volts or even 500,000 volts. That much voltage is needed to push electricity over long distances with minimum energy loss, but it is far too dangerous for direct use. Inside the main tank, the heart of the transformer is the core and winding assembly. The core is made of thin, laminated sheets of silicon steel. Its job is to provide a path for magnetic flux. Wrapped around this core are two sets of copper windings. The windings you see glowing in red and green are the primary and secondary coils. The primary winding receives the incoming high-voltage electricity. As current flows through it, it creates a powerful, changing magnetic field in the core. This magnetic field is the key to how a transformer works. The secondary winding, wrapped around the same core, is placed in this magnetic field. Through a process called electromagnetic induction, the changing magnetic field in the core induces a new voltage in the secondary winding. Because the secondary winding has fewer turns of wire than the primary winding, the voltage comes out lower. This is called a step-down transformer. The green pulses moving through the lower windings represent this new, lower voltage electricity being created. It is now reduced to a safer level, like 11,000 volts or 400 volts, suitable for distribution to neighborhoods. You will also notice the large, curved copper bars and connections. These are part of the tap changer mechanism. Over day, the demand for electricity changes. More people using power means voltage can drop. The tap changer adjusts the number of turns used in the winding, letting the transformer fine-tune its output voltage and keep it stable for consumers. The light pulses shifting through these bars show the tap changer actively regulating the flow. Transformers get very hot during operation because of electrical losses in the copper windings and the iron core. To manage this heat, the entire core and winding assembly is submerged in special insulating oil. This oil does two jobs. First, it acts as an electrical insulator, preventing arcs and short circuits inside the tank. Second, it carries heat away from the core. The large radiator fins you see on the right side of the transformer are connected to the main tank. Hot oil circulates through these fins, cools down with the help of air, and then returns to the tank. The subtle vibration in the animation represents the constant 50 or 60 Hz hum of the core magnetizing, which is normal. At the bottom, the transformer sits on rails with wheels because these units are extremely heavy and often need to be moved during installation or maintenance. The gray tank you see on top is a conservator tank. It holds extra oil and allows the oil to expand and contract with temperature changes without exposing it to air and moisture. So, to summarize the flow you are seeing, high-voltage electricity comes in through the bushings, shown in blue. It energizes the primary winding, creating a magnetic field in the core, shown in yellow. That field induces a lower voltage in the secondary winding, shown in green. The tap changer, shown with red highlights, keeps the output steady. Finally, the new, safer voltage leads through another set of bushings to enter the local distribution network. Without this process, we could not transmit power efficiently or use it safely. Every time you switch on a light, this is the kind of machine that made it possible.